So this lecture is about the application of Coulomb's law with the superposition theorem. So the Coulomb's law says that F is directly proportional to k q1 q2 divided by r square. That is, the force between 1 and 2 is directly proportional to k q1 q2 divided by r square. So this is the mathematical form of Coulomb's law. And what you can see is that you can find the value of k is equal to 9 into 10 raised to 9 farad per meter, and the value of the k is equal to 1 upon 4 by epsilon naught, and the value of the epsilon naught is equal to 8.85 into 10 raised to minus 12 meter per farad. And this was the force of two positive charges, that is, a force on 2 due to 1 when both are positive, and the force will be in the direction from 1 to 2. And suppose the force was q1 here, and it is seen that if it is positive, there would be a field which will be radiating outside of this charge in such a way that it can be shown by these kind of arrows. And if you are bringing another point charge q2 here, then there will be some kind of field intensity on this charge. Field intensity, or the field strength on q2 due to q1. So it is possible to measure what is the strength of the field due to q1 if you are taking the charge q2 as 1. So by extending the same equation, if you are considering the q2 is a test charge and both of these are positive for the test cases, and if you are dividing the charge q2, which is a unit charge, then what you will get is the electric field intensity on 2 due to 1, or the field strength due to charge q1, which can be written as kq1 divided by r square, and in the direction of from 1 to 2. So this is known as electric field intensity, or the field strength or on q2 due to q1, or the field strength of the charge q1. So it's possible to measure the strength of the electric field, which is a vector quantity which could be used due to a point charge, which could be due to a volume charge, or which could be due to a charge distributed on a plane surface or on a line. So to do that, we can simply find the total charge due to the total charge present in the volume, total charge present in the line, or total charge present in the surface area, or total charge due to the point. But again, if you are applying the Coulomb's law on a point charge, suppose q2, and there is the system consists of multiple charges like q1 and q2, so you want to find the force on 2 due to 1 and 3. So it's possible to do that by using the superposition theorem, which we will see. So suppose you are having so this is a application of superposition theorem to Coulomb's law. So you are applying the superposition theorem to the Coulomb's law. So what is there is a point charge, which is, so this is the origin of my system, and the system I am showing by Cartesian coordinate system, which is x, y and z. So I have a point charge here which is q2, I have a point charge here which is q2, and then I have another charge which is q1, and I have another charge which is q3. Now I want to find the total So this is my diagram, and this is not as per scale, this is just to represent. So what I am considering here, so the case which I am considering here is that my first thing is that I have three charges. So there could be a system which will be of more than three charges, which we will just see. So I have three charges, one is Q1, the other is Q2 and Q3. So all the three are the positive charges. So I want to find the force on Q2 due to Q1 and Q3. So if I am seeing my first, so by what superposition theorem is saying that I can find the resultant force by considering each of these charges acting independently. So first I will consider that the system is acting only, the system is having only F1 and F2. So I will find the force on Q2 due to 1, and then I will find the force on Q2 due to 3. So, and finally when I will do summation, I will find the resultant force. So this is my R12, that is the direction of the force on 2 due to 1, and this is my F12. So my F12 from Coulomb's law can be easily written as KQ1 Q2 divided by R12 whole square divided by R12, which is a unit vector, and my force F32 can be easily written as KQ2 Q3 divided by R12 whole square divided by unit vector of R12. So when you are doing the summation, what you will find is that you can take the Q2 common. So you can write KQ2, and what will remain inside is Q3 divided by R12 whole square plus Q1 divided by, or this is R32 and this is R32, Q1 divided by R12 whole square, and the unit vector R32 and the unit vector R12. So this is a general equation which you will find. If you see in the graphical form, it's possible to show that this is my F12 force, and this is my resultant force, while at the same time this is a force F32, and I'm summing F32 plus F12. So what I'm getting is the resultant force, which is this vector which I will be getting. So just erasing this to write it. So what you will get is you will get the force, like you can get the force F resultant. So suppose you are finding the force on which you are finding is the force on a K, and then it will be can be generalized as KQK, and summation of J is equal to 1 to N, and Q of J to, and J is not equal to K, and the vector will be always from R K J. So if suppose my K is 2 here, so K2 and RKJ whole square. Suppose my K is 2 there, so I want to find the force on Q2 due to force on 2 due to 1. So my J is 1 here. So J will never be equal to 2. So generalizing that, my K is equal to 2 there, so it will be KQ2, and this can be written as Q1 because my J is 1 in this case, and R, your K is 221, and your R 21 whole square. So this is how you can apply or generalize or to find out the Coulomb's law due to distribution of point charges. Again, the same thing can be applied to find the electric field intensity. So if you are having a point charge which is Fk, and you can divide it by Qk, and what you will finding is a Ek. It is possible to generalize it from summation of j is equal to 1 to n, while j is not equal to k, and qj into rjk divided by rjk whole square, while the force of Fk was equal to Qk. Fk was equal to kqk, where it was summation of j is equal to 1 to n, and it was going from q of j to r of jk and divided by r of jk whole square. So the thing is that whether you are going from jk, or whether you are considering the unit vector to be jk, or whether you are considering the unit vector to be kj, so this will depend on the direction of the charges. So suppose you are considering that your k is equal to a charge 2 in this case, that is a charge q2, and your j is a charge q1 in this case. So suppose if this is positive and this is positive, and what you are finding is a F2, which is a force on 2 due to 1, and both are positive, then when you're finding the force on 2 due to 1, the force will be always in repulsive, and your distance which you'll be getting here will be r12. So the r12 will be rjk in this case, because this is your j and this is your k. So you'll have to consider the direction of the unit vector based on the polarity of the charges, which is, so if nothing is specified in specific while you are calculating a problem or something, if nothing is specified as to the direction, so it is assumed that all the charges in the system are positive charges, while it is specifically specified that q1 and q2 are positive, while at the same time q3 is negative. So you'll have to consider in such a way. So that's how you will have to consider the direction of the rjk which you are using. If it is rjk which you are going to consider here, or rkj which you are going to consider, based on the direction of the positive charges which you are getting. So anyway, it will not matter when you are considering rjk, the magnitude or the distance, but it will matter when you are considering the unit vector here, which will show the direction. So that's what you want to take into consideration, and the unit of the force will be in Newton, and the unit of the electric field strength will be in Newton per Coulomb, or the electric field intensity will be in Newton per Coulomb. Again here the J will not be equal to K. So that's what you have to consider while you are applying superposition theorem to Coulomb's law to find out force on one charge due to more than one point charges.